All right, so let's explore chemical equilibrium a little bit more. So in 1864, two Norwegian chemists by the name of Goldberg and Vag concluded what about chemical equilibrium? Well, what they said was this. Let's say you have a chemical reaction that you have component A and component B, and these are your reactants, okay? So I'm going to put a plus sign. Now, in front of A and B, you've got stoichiometric coefficients, which I'm going to use lowercase a and lowercase b for. Okay, so again, lowercase a and b, these are the stoichiometric coefficients to our components A and B. Okay, so these will react and form products C and D. Okay, and so the capital letters, these are the products. The lowercase c's and d's, these are the stoichiometric coefficients. So if you have a reaction that looks like this, what Goldberg and Vag concluded was that you could create an equilibrium expression that says this. So we use a capital K, lowercase sub c, where c stands for concentration. Okay, this will be equal to the concentration of the products over the concentration of the reactants. Okay, or what this means for us, the concentration of component C raised to the power of the coefficient C times the concentration of D raised to the stoichiometric coefficient D divided by the concentration of A raised to the stoichiometric coefficient A times the concentration of B raised to little b. Okay, now here's what's really cool about this though. Kc, the equilibrium constant, is constant. Okay, no matter what the concentrations are. So, interestingly, we can say that the variable we just described above has no units. Well, how is that possible? The reason why it won't have any units, because they all cancel out. Kc really is a ratio compared to the standard state. And for us, the standard state is going to be 1. And now we're going to get into this in a little bit. What does that mean? Okay. Now, in addition to the forward expression, we can also write our expression for the reverse reaction and even relate the two equilibrium constants. So let's say you've got this as a forward reaction. So let's say you've got N2, which is a gas, reacts with 2 moles of O2, also a gas, and this is going to be in equilibrium with the product 2 moles of NO2. Okay, so there it is. And if we were to write an equilibrium expression for this equation, Kc would be equal to the concentration of NO2 squared divided by the concentration of N2 times the concentration of O2 also squared. All right. Okay, so that's the forward reaction. If I was to write this reaction in reverse, and what I'm going to do is, let's switch colors. I'm going to do this in red. The reverse reaction, 2 moles of NO2 forms 1 mole of N2 plus 2 moles of O2. So this is just the reverse of the reaction we just wrote above. And so if I was to write an equilibrium expression for that reaction, Kc would be the concentration of N2 times the concentration of O2 squared divided by the concentration of NO2 also squared. Okay. Now, that's really interesting that the reverse reaction, so you get this Kc for the forward reaction, you get the Kc for the reverse reaction. There's got to be a relationship between these two. So what I'm going to say Let me change this a little bit. Let's say for the reverse reaction, I'm going to call this Kc prime. So I'm going to put a prime symbol. And the reason why we're going to do that is I'm going to show you the mathematical relationship between these two. So how are they both related? The forward equilibrium constant and the reverse. How they're equal to each other is that the reverse equilibrium constant, okay, is going to be equal to the reciprocal 1 over the forward equilibrium constant. So that's pretty cool. All right, so key point, a change in what variable is going to cause a change in the equilibrium constant? Temperature. Anytime you change the temperature, even by 1 degree, you're going to get a different equilibrium value. Okay, by the way, the lowercase c in Kc refers to what concentration unit? That is going to be molarity. Okay, so C refers to concentration. Because there's another equilibrium expression that uses pressure. So it's also common to use another form of the equilibrium constant using the unit atmospheres, ATM. And when we do that, when we write an equilibrium expression using pressure, this produces a constant that's written as K sub P, where standard state is 1 atmosphere. So let's try an example problem. Let's see how this works. All right, so let's try this problem out. In the industrial synthesis of hydrogen, mixtures of CO and hydrogen gas are enriched in H2 by allowing the carbon monoxide to react with steam. Chemical reaction for this water-gas shift reaction is the following. Carbon monoxide plus water is in equilibrium with CO2 and H2. What is the value of Kp at 700 K if the partial pressures in an equilibrium mixture at 70 K, or this should be at 700, sorry, not 70, 700 K, are 1.31 atmospheres of carbon monoxide, 10.0 atmospheres of water, 6.12 atmospheres of CO2, and 20.3 atmospheres of H2. Okay, so what I'm going to do, in order to solve this problem, first, we've got our chemical reaction. First thing we need to do is set up the Kp expression. So what I'm going to say is Kp is equal to, now even though we wrote the expression for Kc and not Kp before, writing a Kp is just the same thing. What we're going to do is take the pressure of the products divided by the pressure of the reactants. So in this case, we'll take the pressure of CO2 times the pressure of H2 divided by the pressure of CO times the pressure of H2O. Now, since everything is 1 to 1 to 1 to 1, for the stoichiometric ratios, we don't have to worry. We don't have to worry about, raising anything to a certain power because everything's 1 to 1 to 1. Okay, so let's pop in our numbers. The pressure of CO2, according to the problem, was 6.12 atmospheres. Okay. The pressure of H2 was 20.3 atmospheres. Okay. Divided by the pressure of CO. The pressure of CO was 1.31 atmospheres. And then the pressure of H2O was 10.0 atmospheres. Okay. So if you take 6.12 times 20.3 divided by the product of 1.31 times 10, the number you get is 9.48. All right. So that's how you would solve an equilibrium problem if you know the pressures at equilibrium. Let's try another one. So here's our reaction. SbCl5, which is a gas, is in equilibrium with SbCl3, which is also another gas, plus Cl2, also gaseous. So if we were to write a Kc expression for this reaction, the equilibrium expression would be, for Kc, would be the concentration of the products SbCl3 times the concentration of Cl2 divided by the concentration of SbCl5. Okay, again, it's the concentrations of the products divided by the concentrations of the reactants. Now, what I'm going to do is write the same expression. This time, I'm going to write it for Kp. So the Kp expression would be the pressure of SbCl3 times the pressure of Cl2 divided by the pressure of SbCl5. Okay, now let's say we know the Kp for this expression. So the Kp for this reaction is going to be 1.48 at 448 degrees Celsius. How do we get the Kc value for this? So, in other words, is there a way that we can relate Kc and Kp? So that way, if we know one, we could calculate the other. Well, yeah, there is a way. So let's take a look at this. It's actually derived from the ideal gas law. So if you remember back in Gen Chem 1, the ideal gas law says this, PV equals nRT. All right. So what we want to do is now rearrange this equation in terms of molar concentration. So we need moles per liter. Liter is going to be volume, moles, that's N. So we need to rearrange this equation that has N over V by itself. Okay. So you've got this equation PV equals nRT. We need N by itself first. So let's do that. Let's get N by itself. So you've got RT on the right-hand side along with the N. So we need to divide both sides by RT. So you've got PV equals nRT. Let's divide both sides by RT. All right, so we get this expression. N is equal to PV over RT. Now I need to get V on the left-hand side. So what I'm going to do is divide both sides by V. Okay, and by doing that, I get this expression, that N over V, which is molarity, by the way, is equal to pressure divided by RT. And there you go. So we're going to need that. So essentially what we're going to do, in order to get molarity, which is N over V, I need to pop this expression in for each of our pressures. So it's going to be the pressure of SbCl3 divided by RT. And then the pressure of Cl2 divided by RT. So if I was to rewrite everything, here's what it would look like. The Kc expression using the Kp values would be something like this. You're going to have the pressure of SbCl3 divided by RT times the pressure of Cl2 divided by RT divided by the pressure of SbCl5 divided by RT. Okay, I'm going to make a line so that way that V is not part of this expression. All right, cool. And so we know that P divided by RT is going to give us molarity, and so we're good. Okay, now let's see if we can find somehow the expression of Kp from above and extract that out. So remember that Kp was this. Kp were all the pressures. Okay, so what I want to do is extract this expression out of what we got here. All right, so this is where it's going to get a little ugly. So if I was to do that, rewrite this expression Kc and see if we can extract the Kp, what that would look like, Kc would be equal to Kp times 1 over RT times 1 over RT, because you have two products, divided by 1 over RT for the one reactant. Okay, now we can actually simplify this a little bit more because this denominator is going to cancel out with 1 over RT's, one of the products. So now we would get that Kc would be equal to Kp times 1 over RT. All right, so given what we just derived and the specific value of Kp, what if we were to calculate Kc from this? Okay, so Kc for this reaction, remember the Kp value was 1.48, and that was given to us originally, times 1 over, okay, so the R we have to use, because we're dealing with gases, we have to use the universal gas constant, 0.0821 liter atmosphere over kmol, times the temperature which we were told that the temperature for this process was 448 degrees Celsius. Okay, but we need to convert this to Kelvin, so we need to add 273 to convert that to Kelvin, and then you're good to go. All right, so once we were to take 1.48, let me get my calculator out. If we take 1.48 times the quantity 1 divided by 0.0821 times the temperature, so let me put this in another parentheses, 448 plus 273. All right, so that would give us, the grand total would be 0.025. All right, so we don't quite know what those numbers yet. What if this means that, what these numbers quite yet. We know it's a ratio compared to 1, but we don't know what that means quite yet. We're getting close to that. All right, so we just derived for this particular reaction a way to start with a Kp value and then calculate Kc out of it. So there's a relationship here between Kc and Kp. So the general relationship between the two, because this is what we just did, works for only this problem. The general relationship is like this, that Kp, the pressure, the equilibrium pressure, is going to be equal to Kc, the equilibrium concentration, times the constant quantity RT, raised to the delta n power, where delta n is going to be the stoichiometric coefficients. So C plus D, the coefficients of the products, minus the coefficients of the reactants, A plus B. Okay. Now, keep in mind, this only works if all the species are gases. So that only works if all the species are gases. What happens if you don't have a gas? Well, good question, because guess what we're going to talk about next. So let's go into another example. So let's write the chemical expression for the decomposition of solid mercury 2 oxide to produce liquid mercury and oxygen. And by the way, this was how oxygen was originally produced in high school chemistry labs. Okay, clearly we don't do this nowadays because mercury is not good for the environment, so we don't really do this. But what chemistry teachers used to do was take 2 moles of mercury 2 oxide, HgO, okay, and they would decompose it to form 2 moles of liquid mercury plus 1 mole of oxygen gas. Okay, now if I was to write the Kc expression, so it's telling me, right, let's write the expression for Kc, but let's put quotation marks around it. Now there's a reason why we're doing that and I'll explain why in a second. But if we were to write the equilibrium expression for that, we would have the concentration of Hg squared times the concentration of O2 divided by the concentration of HgO squared. Okay, so that would be the equilibrium expression for that reaction. Now, there is a problem, though. There is a problem with this. And the problem is that we don't include pure liquids and solids in equilibrium expressions. So we don't include pure liquids and solids in equilibrium expressions. And so that's the problem with this particular expression, and that's why we have quotation marks around Kc. But let's jump into this. All right. Now, since we know that mercury has a density of 13.6, grams per milliliter, we can actually calculate the concentration of mercury in moles per liter. And so that would look something like this. The concentration of mercury, which is going to be the number of moles divided by volume, we know the density is going to be 13.6 grams per 1 milliliter. And if we were to convert the mass from grams to moles, we would have 1 mole of mercury over 200.6 grams. And if we convert the milliliters from milliliters to liters, that would mean 1,000 milliliters over 1 liter. Okay, so units will cancel out. So the units that we're left with is going to be moles per liter. And so the answer would be something like 67.8 molar. So that would be the concentration. Now, we could do the same thing for the solid reactant, but what this means is that the concentrations of mercury and mercury 2 oxide, because they're pure liquids and solids, they're constant. So that means that the values can be combined with Kc. All right, so here's what we got. Remember, we had this. Kc is equal to the concentration of Hg squared times the concentration of O2 divided by the concentration of HgO. And this is also squared. All right, so if that means that the mercury and the HgO are constants, then they need to be combined with the Kc. So if I do that, if I multiply both sides by HgO squared, I get Kc times the concentration of HgO squared is equal to the concentration of Hg squared times the concentration of O2 squared. Okay, now because Hg squared is also constant, I need to move that to the left-hand side, so I need to divide both sides by the concentration of Hg. So I would get this, that Kc times the concentration of HgO squared divided by the concentration of Hg squared is going to be equal to the concentration of O2. So that means what this all means is that Kc, the real Kc, is only going to be equal to the concentration of O2. So what is the significance of this conclusion that we're talking about? That means that temperature, based on what we just did, there's two things that we need to get out of this. First thing is that temperature will affect the equilibrium constant. Okay, so that's the first thing. The second thing, when we calculate equilibrium, Kc can only be done, or it can only be calculated for gases or aqueous solutions. So this is going to be really important. That's what we're looking for, gases or aqueous solutions. So we're coming really close to the heart of this chapter. But before we can do that, let's do a little bit of cleanup because I have introduced some concepts and then I walked away from them. So let's do just a little bit of cleanup before we really dive into the material. So remember that one of the reactions we looked at was SbCl5 breaking down to form SbCl3 and Cl2. And everything's gaseous, and this is in equilibrium. So the products are in equilibrium with the reactants. Okay, and then we also wrote an equilibrium expression for this, that the Kc was the concentration of SbCl3 times the concentration of Cl2 divided by the concentration of SbCl5. Okay, and for this reaction, we calculated it to be 0.0250. Okay, so here's what we want to look at. Let's consider an equilibrium mixture of these three components. If the concentration of SbCl3 is equal to the concentration of Cl2, and the concentration of both of these are 0.05 molar, let's find the equilibrium value for the concentration of SbCl5. Okay, so again, we have our equilibrium expression up here. We know what Kc is, and we know the two concentrations of the products. The only thing we're missing is the concentration of SbCl5 at equilibrium. So that's what we're going to solve for. All right, so let's pop in the values that we know for this problem. So we know that the concentration of SbCl3 is 0.050 molar. The concentration of Cl2 is also 0.050 molar. And the concentration of SbCl5, that's what we're looking for. All right, and then this is all equal to 0.0250. All right, so we need to solve for the concentration of SbCl5, and the only way to get it by itself is to multiply both sides by that concentration and then divide by 0.0250. So let's do that. Let's multiply both sides by the concentration of SbCl5. Okay, so that way it cancels out from the denominator on the left. And so that should give you 0.050 molar times 0.050 molar. Okay, and that's equal to 0.0250 times the concentration of SbCl5. Okay, so I want to divide both sides by 0.0250 this time. Okay, and then that allows us to solve for the concentration of SbCl5, which is going to be 0.050 times 0.050 divided by 0.0250, which should be, the concentration of SbCl5 should be 0.100 molar. Okay, so that's how you would solve for the concentration at equilibrium for one of the reactants. We could do the same thing for a product. If we know all the concentrations at equilibrium, we can solve for Kc. Not a problem. All right. So doing the calculations at equilibrium is not that difficult, but it's more common to know the starting concentrations and wanting to know the concentrations at equilibrium. So that's where we're going to go next. All right, so to help us to identify where a reaction is at, I've got to introduce a new quantity here. So starting with the same equation, SbCl5 is in equilibrium with SbCl3 plus Cl2. Okay, here's our problem. The initial concentration for the problem is that the concentration of SbCl5 is 0.150 molar, and because it's initial, there's no product, so concentration of SbCl3 is 0 molar, concentration of Cl2 is 0 molar. Okay, so initially, is the reaction at equilibrium? No. And the reason for that, there are no products. Okay, so that's easy. But what happens when you start getting products? How do you know if a reaction is at equilibrium? We have to, in order to help us figure out where we're at and how close we are to equilibrium, we have to calculate this new variable called Q sub C, which we call the reaction quotient. Okay, and this tells us if the reaction is at equilibrium, or if it's got to move forward, or it's going to move backwards in order to hit equilibrium. So at equilibrium, the reaction quotient, QC, is going to be equal to the equilibrium constant, Kc. If the reaction has to move forward to reach equilibrium, that means QC is going to be less than Kc. And if it's got to move backwards to reach equilibrium, that means QC's got to be greater than Kc. All right, so to calculate QC, same deal, same setup as we did the equilibrium constants. Okay, so for the initial conditions, okay, for the initial conditions, let's calculate the QC. So QC is going to be equal to the concentration of SbCl3, which is 0 molar, times the concentration of Cl2, which is also 0 molar, divided by the concentration of SbCl5, which is 0.150 molar. Okay. All right, so 0 times 0 divided by 0.150, that's going to give us 0. So definitely, since QC is definitely smaller than the equilibrium, which is 0.0250, that tells us, yeah, this is not at equilibrium. Okay, now here's where the next part gets in. Let's assume the reaction moves forward and produces the concentration of Cl2 to be 0.01 molar. What is QC? All right, so what I'm going to do, I'm going to set this up as a table. So what I'm going to do at the top is write the reaction. So we got SbCl5 is in equilibrium with SbCl3 plus Cl2. Okay, so that's my reaction at the top. So what I'm going to do, right underneath that reaction, I'm going to put one row. So this is going to be my initial concentration. So I know initially I have 0.150 molar of SbCl5, and I have 0 molar concentration of SbCl3 and 0 molar concentration of Cl2. Now, what this is saying, though, is that the concentration of Cl2 is going to go up by 0.01 molar. So what I'm going to do is let's make another row. Let's look at delta. Let's look at the change. So we know that Cl2 has to go up by 0.01 molar. Okay. All right, so if Cl2 is going up by 0.1 molar, you can't produce Cl2 and not produce SbCl3 at the same time. So if you're producing one, you gotta produce the other. So in that sense, the concentration of SbCl3 is also going up by 0.01 molar. Okay. Now, if the concentrations of the products are going up, that means the concentration of the reactants have to be going opposite. They have to be going down. So the change is going to be 0.01 molar for the SbCl5. So if I was to add up everything that we got here, the new concentrations for SbCl5 would be 0.140 molar. The new concentration for SbCl3 should be 0.01 molar. Let me erase that and rewrite that. So the concentration for SbCl3 should be 0.01 molar, and the concentration for Cl2 should be 0.01 molar. So if we calculate the equilibrium, the QC, the reaction quotient for this, for SbCl3, it would be the concentration would be 0.01 molar. The concentration of Cl2 would also be 0.01 molar. And then the concentration of SbCl5 would be 0.140 molar. Okay. And now if you take 0.01 times 0.01 divided by 0.140, that should give you 7.14 times 10 to the minus 4th. All right, now looking at this value, is this lower or is this higher than the Kc? Well, this is still lower, so we're not at equilibrium, okay? And we know that the reaction quotient is still smaller than the equilibrium constant. So we know that the reaction is moving towards the right. It's moving to make more product. All right, so let's do the same thing now. Let's do the same thing, but what if the concentration of Cl2 is 0.02 molar instead of 0.01? How close are we getting? So I'm going to set it up the same way. I'm going to rewrite the reaction. So I'm going to make a table. Okay, so SbCl5 is in equilibrium with SbCl3 and Cl2. Okay, so initially you have concentration of SbCl5 is 0.150 molar, concentration of SbCl3 is 0, concentration of Cl2 is 0 molar. Okay, so the change, if Cl2 is going to go up 0.02 molar, that means the concentration of SbCl3 must be also going up by 0.02 molar, and the concentration of SbCl5 must be going down by 0.02 molar. So that way, if we subtract and add, you've got the concentration of SbCl5 should be 0.130 molar, concentration of SbCl3 should be 0.02 molar, and the concentration of Cl2 should be also 0.02 molar. So if we were to put that into our reaction quotient this time, we would have 0.02 molar for the concentration of SbCl3. Now, since it's the same since the concentration of Cl2 is the same as the concentration of SbCl3, I'm just going to use a shortcut and just write squared, because of the concentrations are the same divided by the concentration of SbCl5, which is 0.130 molar, and the reaction quotient comes out to be 3.07 times 10 to the minus third. So we're still not at equilibrium. Okay, we know that the reaction, because QC is still smaller than Kc, we know that the reaction is still proceeding to products. So what direction will the reaction be going at this second step? We know it's going towards products. Okay, now we can keep doing this. We can keep popping in and saying, okay, well, Cl2 is going to change by this much, or SbCl3 is going to change by this much, and then try to figure out, by plugging and chugging, see where these numbers, see where everything falls in once we get to equilibrium. So we could do it that way, or there's a much more streamlined version which gets us the concentrations at equilibrium, and basically in solving the problem one way, we can get those concentrations at equilibrium and we're good to go. But in order to solve for the equilibrium concentrations, we've got to go back and rely on something from math. And so that's what we're going to do in our next video. Let's review some algebra.